Hi guys, welcome to the second lab lecture where we're going to be doing grain size analysis remotely. And just this lecture is just going to go over, highlight some of the important aspects of polycrystalline and grain size analysis. And this image that you can see over here is of different grains that I imaged in the material that I was studying, nickel titanium niobium in grad school. And this methodology is known as an electron backscatter diffraction pattern, which you get from a scanning electron microscope. And then this is a pole diagram, which we'll take a look at. It's basically showing, what basically means is that the different colors have different orientations over here, and then over here you have the software which is delineating the grain boundaries. All right, so why are we, why are we looking at the microstructure? We're looking at the microstructure because it's really the microstructure that dictates the properties of how a material behaves, right? And it goes back to biology, when the first biologists, including Leeuwenhoek, and others, started using microscopes to look at the internal structure of plants, and they saw that they were made up of cells. And then similarly, a very famous geologist, Sorby, was one of the first to make cross sections of iron and other stuff and polish them down and grind them down and etch them out. Look at them, that even metals and materials had very similar, they were also made up of cells, but they weren't really cells. They were grains, as we know now, right? So to define what really is the microstructure, right? The reason it's called a microstructure is because it was a structure that was observed inside a microscope, right? And this is basically in contrast to what we know now, that the crystals are what make up the materials, and which are approximated as the collection of atoms. The microstructure is more so beyond the crystal structure, right? So what we looked at in chapter 4 was that it's the defects that really define us. So the microstructure is the crystal structure with the defects, and it's the existence of these defects as grain boundaries, as point defects, as vacancies, as surfaces that really define how the materials that behave, right? So the defects that we are mostly interested in our course are the interfacial defects, which are grain boundaries, and we'll take a look at what interface boundaries are later on, and dislocations, and also point defects. And since the most important unit when we're looking at microscopes is a micrometer or micrometer, right? That's 1 micron, so 10 to the negative 6th meter. And it also happens to correspond to, it's the wavelength of light between 300 to 700 to 800 nanometers, some of that. Fair enough, fairly close to what a micrometer is, right? So microscope uses light, micrometer fairly close enough to light. Thus microstructure is really the unit that we use for at the scale of stuff that we're looking at in the microstructure of materials that we're interested in. And we basically, since we've been observing these in metals, we mostly see grains as crystallites and polycrystalline material, and these grains are separated by grain boundaries. Oh, I forgot to give a shout out to Carnegie Mellon University, where I got a majority of these slides from, right? So when you have a random material which is just cast without doing anything to it, having any directional flow of the liquid material, the material crystallizes in this polycrystalline form, where all of these polycrystals are their own single crystal, and they are all oriented in different directions. And these directions here basically signify a close packed direction of that crystal structure. And you can quantify that using electron microscopy, and as we saw, electron backscattered diffraction pattern. And these colors, basically, we don't need to get into this, is a little bit more in grad school level stuff, but the colors basically mean that they're in different orientations. And the more distributed the colors are, the more random the distributions are. This is what's known as a pole figure, which is what's used to allocate the color. And these 3 directions, which we're now familiar with, are basically, or the 3 main different distinct directions in which the close packedness can occur. So this pole figure and these colors are used to define these different grain orientations. So The more distribution you have in this RGB spectrum, the more randomly oriented the different grains are. And that what that ends up meaning is that on a larger macroscopic scale, there the material is isotropic. What that means is that the grains are not preferentially oriented in a particular direction, right? So this is what an isotropic material is, which basically means that because of this random distribution of polycrystalline grain directions, macroscopically, the mechanical properties are independent of direction. They're same in all the directions. So that's what makes up an isotropic material, right? So when the material is isotropic, what that means is in material science, we say it has no texture. Texture means basically when these polycrystalline, these grains are preferentially oriented in one direction. And this happens when you roll the material and you go through a manufacturing process where there's flow involved and you're making the crystal solidify and you're orienting the crystals in certain directions, right? So this is what a schematic for a texture would look like, right? So we know that blue corresponds to the 111 direction. So you have these close packed directions in these crystals, which are all close to that 111 direction. If all of them were exactly 111, then it would be a single crystal, right? But they're all moving towards being in that 111 direction. So you can say that these grains have a 111 texture, and that's what it means. And that makes these materials anisotropic because their properties are going to be related to the distance of this, in this direction. They're going to be different than in other direction because they're not randomly oriented anymore. All right. We'd already seen what a grain boundary was, but it's basically the atomic packing being disrupted due to a change in the lattice direction of the two different crystals that you have in a polycrystalline material. And in all crystalline solids, most crystalline solids, the grain boundary is it's very thin. It's around one or two atoms, right? And there's a lot of interfacial energy as well, which is similar to surface tension, and that's what is the hot topics of research which have been going on for a very long time, right? So in order to define these structure property relationships and start tailoring these microstructures to have the mechanical behavior that we need to be able to quantify the microstructure, right? And one of the most important quantifications that you can do is to find out what the sizes of your grains are, because then by doing heat treatments, you can do recrystallization. By doing rolling, you can change the dimensions in certain directions, and then you can end up changing the mechanical properties of them. So the first step is to figure out how we want to look at these microstructural images of grain boundaries and how we go about quantifying them, right? So that's what we're going to take a look at in this lecture and for your assignment. So there's a couple of different ways you can look at area count. So you can look at linear intercepts, and these methods really stem from, they're more so an old school way of looking at things, because now we can just use image processing software like ImageJ, and just put in our grain sizes, our grain microstructure, grain images in there, and they will just automatically spit the data out about what the average size is, what the distances are, and stuff like that. But before that was possible, even as far as 1996 was when the ASTM standard came about for figuring out what the grain sizes are. And this standard basically assigns a grain size number, which is directly related to the size, that, as we're going to see. And we are going to take a look at this linear intercept method of how to find out what the grain sizes are and what this grain size number is. So this grain size number is just this method used by the ASTM to kind of normalize the measurements of grains across all different materials. And it's just make things easy. You just have a simple number associated with grain size that you can then use to kind of see like what happens when you do these heat treatments, or what happens when you do this kind of rolling, and then in the different directions as does the grain number change, and other things like that. And I encourage you to go to this link to find out some more information. right? So instead of, so these intercepts give you an idea of what the size is of the actual size of the grains, but then this grain size number makes it easier to do these comparisons later on. And this is the standard is called E1112. And it can be based either on area or on the linear measurements. And we are focusing on this linear measurement, right? And as I said, that this, because it's a standard, it's very commonly still employed within the industry and in older research efforts. But if you look at research papers in the more modern day over the past decade or so, you'll see that you just have the grain size directly stated. You don't, researchers don't use the grain size number too very often anymore, because they just use software to automatically tell them what the grain sizes are. But in industry, things are a little bit more old school, and they, especially in the steel industry, they still use the grain size number a lot. And in general, the rule of thumb is that a higher grain size number means a smaller grain size overall. And this is the formula, this last one over here, the one that we're going to use to convert what the average length of a grain is to the grain size number, as we'll take a look at in the example that we do. And also I'll upload the E12 standard for you to see. And this is the grain size relationship between the area and the mean intercept. You know, it's just basically they've just taken this formula and listed out the grain sizes for different, an increase in grain size, and then what the corresponding uh, average grain area, grains per unit area, mean intercept, and lengths and etc. of these things are. So let's find out how we play with these things, right? So you can, when you're given a microstructural image of grains, you are, you know, the question that they can ask you is, find what the mean intercept length is and find out what the grain size number is for me. All right, and the way that we do that is that, let's see, if we go to our, this guy. So this, for example, that this is the image that you want to see, right? So the first step is capturing the image. So what I do is just do print screen, take it over to Paint or your other image processing software of choice, select just the area that you're interested in. And I'm showing you how to do this in PowerPoint, but you can do this using other software too that you would like. Right? And then paste that image back there and make sure that if you're going to resize it, that you fix the aspect ratio so that if you change one dimension, the other dimension changes as well. Like that did not happen. That was not supposed to happen. So lock aspect ratio. There we go. All right. So that worked out okay. Let me make it a little bit bigger. All right. The next thing to do is to figure out what your magnification is at this image that you're looking at. And for that, we use the scale over here, right? So we know that the scale in the real image is 100 micrometers thick. But right now for this image that we're looking, what is it? So you can just go to PowerPoint, draw that line out, which is approximately the same length, and then go to its size and see that it's 4.66 millimeters, which is basically just going to equal how many micrometers? So 4.66 centimeters to micrometers is equal to 46,600 micrometers. So make sure that when you're finding out what your magnification is, and that's the first step, that you use microns, all right? So you go and write that that guy is equal to 466,000 micrometers. And this is why the units have to be the same, because the magnification is just going to be a number, right, that you take. So then you see that this picture was taken at 466x. Okay. Then the next step is you have to draw an n, let's say you have to draw an appropriate number of lines, and an appropriate number of lines is somewhere between 5 to 15, but we're just going to use 7 for this example over here. Then what you do is that you go ahead and you draw these lines. Just draw one of them, and then we'll use the same one to orient it differently. What we're basically going to do is take this line and just make it have different orientations where it's completely contained inside the microstructure. So if we go and let's make sure that it has a nice length. So if we go to the size. See, this one is 9.53. Let's just make this 8 centimeters. That just makes things easy. And then what, you can also do this by hand. So print it out and draw these lines out by hand. That's totally okay. So I'm going to go ahead and make 7 copies of this. 2, 3, 4, 5, 6, 7. And then you want to randomly orient them, right? So you just go to here, maybe make that 25 degrees, put that line there, like that. Maybe orient this guy 80 degrees. Go put this guy over here. Maybe orient this guy by minus 30 degrees. That guy is like that. So what we're going to do is basically with these lines, we're just going to randomize these lines across, see how many intercepts they have. And with this randomization, we get like an average kind of idea of what the grain size number is going to be, if that makes sense. So let's say minus 60. So that's what that guy looks like. So let's put him right there. Let's take this guy and orient him just a slight bit. And you want to like try to capture as many different locations as possible to, again, increase what the odds are going to be. And then for the last line, let's have it go at 55 degrees, or rather minus 55 degrees, like that. And we make it a little less, minus, say, 45 degrees, like that. There we go. All right. So now we've drawn out the 7 lines. Now what we say is, now we go line by line and count out the number of grain boundaries that they intersect. So if we take a look at this line, you never count the edge of your picture, because that is not the grain boundary. That's just the edge of your picture. So and make sure that your line is inside, right? So the number of points at which this guy intersects is 1. I'm going to count that as 1, 2, 3, 4, 5, 6, and 7. So this one intersects 7. So that's number 1. This guy is number 2. This guy intersects 1, 2, 3, 4, 5, 6, 7, 8. Let's say that that's 8. All right. So I've done this line and that line. Then we go to this guy here. That guy has 1, 2, 3, 4, 5. 5. Okay, so 1, 2, 3 is done. Let's go with this guy. This guy has 1, 2, 3, 4. I'll count that as 1, 5, 6, 7. So this guy has 7. Okay, so then 1, 2, 3, 4. Let's do this guy. This guy has 1, 2, 3, 4, 5, 6, 7, 8, 9. Say that guy has 9. Okay. Then let's do this guy. This guy has 1, 2, 3, 4, 5, 6, 7. 7. And then we do this last one, which was our first one. 1, 2, 3, 4, 5, 6, 7, 8. So this guy has 8. Then what we do is, from these 7 lines, you have all of these, just sum them all up, right? So it's 7 plus 8, 15, 20, 27, 36. 36 plus 7 is 43, right? 43 plus 8 is 51. So you end up with 51 total intercepts, right? Then the next step is to figure out what the overall length is going to be. So because the length of each line was, we set it to be 8 centimeters, right? So that guy was equal to, let's say, each line was 80 millimeters, which is the same thing as 8 centimeters. So the total line length of all 7 lines is the number of lines. So this guy is called L subscript T. So 7 times 80. And that is equal to 7 times 80 is 560, right? Yep, so that's just, so if you want to use units, it's per line. This is 7 lines. This is millimeters per line. Cancels out, 7 times 80. You end up with 560 millimeters, right? And then the mean intercept length, the first one, which gives us an idea of what the grain size is going to be. This is the formula for it. So the mean intercept length, which is characterized by that fancy L with a bar on top, is just equal to this LT divided by P times M, where M was that magnification that we'd found, and P is just equal to the total number of grain boundary intersections. So P is grain boundary intersections, and M was the mag, right? So now we know everything. So LT is equal to 560 millimeters. The number of grain boundary intersections was, how much was it? It was 51. The magnification was 466. So we do the math, and that number turns out to be equal to 60 divided by 466. So you get 0.0236 mm, or you can convert this to microns, which we like. That's 23.6 microns, right? So that's the mean intercept length. So that gives you an idea of what the average grain length, so to speak, is, right? And then the next part is to figure out what your grain size number for the STM is, so that the people in industry have an easier thing to look at. And for us, with the intercept length, which is given in millimeters, so remember, so this is with your average intercept length in mm. This is the formula for it. The grain size number is equal to G minus 6.6457 and log base 10. That's the other thing you got to remember, of L minus 3.298. Just to make sure. Yep. All right. So now we just plug that in. 6457 log base 10 of, and remember, you're putting this in millimeters, so 0.0236 minus 3.298. So the grain size number ends up being, need my calculator for this one. So on, so minus 6.6457 times log of 0.0236. 0.298. So it's 7.5, right? 7.515, but because the STM standard, you can leave the answer like this and it's totally fine, but the STM standard likes it in 0.5. You don't need to do this part. So the grain size number is equal to 7.5. All right. Okay, and there's another kind of math that you can do to kind of relate your grain size number to your area measurement, right? Because we have that formula as well. So let me just bring my note ins for this one. Hang on 1 minute. So the equation that relates the grain size number to uh, the the average number of grains per square inch is equation 4.18, and that's basically NM times M over 100 squared, and that's equal to 2 to the power of G minus 1, right? So what are the different things here? So NM is equal to the number of grains per square inch at that magnification M, right? And we know what M and G are, right? So M is just the magnification, and G is the grain size number, right? So in our problem statement, we're told that NM is equal to 25 grains per square inch, right? All right, and we're told that M is equal to 600, right? So what we have to find out is what this, so we know that we have to just find out what G is, right? And that's just mathematical manipulation at this point, right? So what we do is we just take the logarithms on both sides. So let's take natural log. So you end up with log of nm times m over 100 squared is equal to the log of 2 to the power of g minus 1, right? And then we just use the properties of log, right? So what we can do is that we know that log of AB is equal to log A plus log B. So we can say that that expression ends up being ln of nm plus ln of m over 100 squared. And that guy is just, so the exponent comes out, right? So we can just say that that's equal to g minus 1 times ln of 2, right? And this 2 can also come out in front, so I'm just going to do that. That guy is over there, right? So essentially, rearranging this guy, I see that my g is just going to equal what? It's going to equal ln of nm plus 2 ln of m over 100 divided by ln of 2 plus 1. And plugging everything in, just get ln of nm, which is 25, plus 2 times ln of 600 over 100 divided by ln2 plus 1. You do the math on that, and your g just ends up being equal to 10.8. And again, as I said, you want to relate this to the closest number, but for us, we can, leave it as it is. So yeah, that's it for this week's lecture. The assignment has been posted. Make sure you take a look and let me know if you guys have any questions. So the assignment is going to be due next Tuesday. So you have 1 week to hand it in. All right, thanks.